ready to go.
Great. I'll let you handle all the folks running in the room now.
Yep, you bet.
Sure. So welcome back to this semester's AOS Colloquium. I'm very pleased to welcome back Dr. Val Bennington to the Atmospheric and Oceanic Sciences Department. Val received her BA in Mathematics from Connecticut College and her PhD from this department, working with Galen McKinley on topics of ocean biogeochemistry around 2010. Afterwards, she stuck around this building for a bit. She completed a postdoc at the Center for Climatic Research and then later transitioned to do an atmosphere assistant scientist role, working on topics related to climate change on the Laurentian Great Lakes in the North Atlantic Ocean. After that, she applied her technical skills to something totally different, software outpatient health records at Epic Healthcare Systems. First working nearby from Verona, Wisconsin, then later for 3 years in Bristol in the UK, and then she worked on records for healthcare organizations all around the world. In 2020, she returned to academia and is currently a postdoctoral scholar working at Columbia University remote from Hilo, Hawaii, on physically based machine learning approaches to understanding the future of the ocean carbon sink. Which is something she'll be telling us about today. She'll be pausing a few times through the talk for questions, so hold your questions to those moments or put them in the chat at any time, and Pete and I will try to moderate them. With that, I'd like to welcome a warm virtual welcome to Dr. Bennington.
Thank you so much. It's really nice to be here and to virtually see everybody at UW. I'm sorry I couldn't be there in person, but we all know how COVID goes. And today I'm going to talk about reconstructing air-sea carbon dioxide exchange using machine learning and get into does incorporating physical knowledge help reduce any sampling needs. I'm going to start by acknowledging Professor Galen McKinley, who is now at Columbia and Lamont, who gave me this awesome opportunity to get back into science I'm working with right now. A couple other professors there who specialize in machine learning, and some students, postdocs, and Data Science Institute scholars I've been working with. So I'll start with an introduction to the ocean carbon sink and discuss the large ensemble testbed that we're using in this technique to understand our techniques. I'll then talk about incorporating physical knowledge into a machine learning based reconstruction. And then I'll finally talk about sampling experiments that I'm working on and where I hope to go in the future. So we probably all know that the ocean is a very important carbon sink for our planet, with about a quarter of all of the CO2 emissions from the last decade being absorbed by the ocean. But how can we quantify the amount that's absorbed by the ocean each year and how it varies from year to year, where this is going, and how it might change in the future? So we use both models and observations to estimate historical CO2 fluxes. And I'll go a little bit into the processes here. So what controls the ocean carbon sink? So we have both the biological pump and the solubility pump. So sorry if I look at my screen, it's just I'm looking at my other screen. The biological pump involves basically the phytoplankton of the ocean. So as the phytoplankton grow, they absorb and take up CO2 gas from the surface ocean, build carbon into their bodies, and then through waste production are actually removed into the deeper waters. So a portion of the biological productivity ends up removing carbon from the surface ocean to the deeper waters away from the atmosphere. The solubility pump, on the other hand, is, to put it simply, colder water can hold more CO2 gas. So if you have water in something like the jet stream moving along and cooling as it goes, it's able to actually absorb carbon dioxide from the atmosphere as it cools. We also have, of course, deep water mixing and ventilation. When deep water is brought in contact with the surface, we have old carbon coming to the surface and actually emitting to the atmosphere. One thing I want to mention is, I will say a lot, is PCO2. That just stands for the partial pressure of carbon dioxide gas in the surface ocean. So ocean biogeochemical models actually use these processes we know and simulate them to estimate the ocean carbon sink, whereas our data products use observations to reconstruct the ocean carbon sink. So how do they agree? What does it look like now? So on this plot in blue are the data products that are currently being in use. And in black are all the different ocean biogeochemical models that are part of the global ocean carbon budget. On this axis is actually increasing, means a larger sink of carbon that going into the ocean. And what you'll notice is they look similar in pattern. Year to year ups and downs look similar. However, the data products are estimating a larger ocean carbon sink than the ocean biogeochemical models. And we'd like them both to agree. So this is not a closed problem, I should say. It's still uncertain what the actual number is. We kind of have a range of understanding here. So what's used in these data products? How are we going from the observations we do have to actual global coverage or a global estimate of this ocean carbon sink? So we're observing PCO2 actually in the surface ocean. And on the left-hand side, you can see the number of months of data over the past approximately 40 years that we have an observation at a given location. And so what you'll notice right away is that the Northern Hemisphere has some blues and some greens. So we've observed maybe 3 years, 4 years of months in that time. The Southern Ocean, the Southern Hemisphere and the Southern Ocean are much, much, much less observed. So you'll see maybe a few months up to maybe 12 months at most ever really observed in those locations in this database. And on the right-hand side, you see the number of unique months with data. That's just to say, what kind of seasonal coverage are we getting? Are we always there during the same month of the year? Or do we, are we going in spring, summer, winter, and fall? And what you'll notice there is that the Northern Hemisphere has pretty good to very good seasonal coverage, whereas the Southern Hemisphere is really sampled only probably during good weather months primarily. But what does this data look like? So I'm just showing here on the left-hand side, Northern Hemisphere winter, December, January, February, the average PCO2 in the surface ocean from these observations during those winter Northern Hemisphere months. And on the right-hand side during July, August, and September. And what I want you to take away from this plot is that this is actually a pretty heterogeneous pattern in both space and time. So you'll notice the equatorial Pacific is very red or as high PCO2. That's a location that actually puts carbon dioxide into the atmosphere. And you'll notice that there's a seasonal cycle of PCO2. It varies throughout the year, whether the actual magnitude of this partial pressure in the surface ocean at other locations. So in the subpolar regions, you'll see higher PCO2 in winter, actually, where there's deeper mixing, bringing up high carbon waters, and lower PCO2 in summer, whereas you see the opposite in the subtropical regions. So how do we go from this heterogeneous pattern in both space and time to an estimate of the actual carbon fluxes throughout the space and time? Right? So typically, an example data product approach is to use a neural network. And the neural network is a machine learning approach that samples the data and then trains a neural network on that data. But what it's actually trying to do is come up with a nonlinear function that predicts ocean PCO2 based on observations we do have. So we do have satellite sea surface temperature. We do have salinity and mixed layer depths and chlorophyll from space, and we know atmospheric CO2 values. So how do those relate to the PCO2 observations in the ocean? So the neural network is used in this example to relate those observations we do have to PCO2 that we want to predict. Once we've actually developed a function between those observations, we can calculate well, we can reconstruct PCO2 everywhere in space and time and then calculate the flux from PCO2, as the flux between the air and the sea is driven by this partial pressure of the carbon dioxide in the surface ocean. So this is a typical approach in a data product. What is, I'm going to get into the basics of what the machine learning is in this process, just so you have an understanding of the basic technique. So this is an example of supervised machine learning. That just means in this case, we have examples of the output we'd like to see from our model. So in other words, we have observed PCO2 in some locations. So supervised machine learning just attempts to classify or quantify outcome based on previous knowledge. A typical traditional programming, you give your computer inputs, but you also give it the function you want to be computed, and then the computer gives you the outputs. So a simple mx plus b, you give it the mx plus b, and you give it an x, and it'll tell you the y. But machine learning, instead of trying to give you just the output, it's actually creating a function given both examples of both input and output, finds the relationship between those two, and creates a model. So it's another type of model. In our example, satellite observations and other in situ data products of the ocean are our inputs. We call these features. PCO2 is what we're trying to quantify, and that's our output. And we give a subset of all of our features and our PCO2 into the machine learning, and it creates the function or the model that is the output. So the model that's output from machine learning can be as simple as a linear regression or as complex as a neural network. And to train our model, or to create the model, we provide it with the features and the known PCO2 using approximately 80% of our data. So from that SOCAT sampling database, we're going to utilize about 80% of it to build our model. And the remaining portion, the other 20% we did not use to build our model, we used to test how well that model generalizes to other data. So how well does that generalize to the data that the model has not seen yet? And we do this with test statistics. So root mean square error, bias, the correlation between the two, and the mean of the absolute value of the error. So there are, of course, just like there are limits to biogeochemical models, there are, of course, limits to our database reconstructions. What you'll see here on the right is you'll see histograms of the observations taken by decade. And what you'll notice is that in the early portions of the database in the 1980s and 1990s, you have far fewer observations. There's a perception that machine learning approaches are black boxes. They're harder to interpret. And how can they be evaluated? What you saw in our SOCAT sampling database is that there are a lot of regions of the ocean that have never been sampled. So they don't show up in our training data set, and they don't show up in our test data set. So how well can we know how well they're doing if we've never sampled that area? And we also have a desire to incorporate the physics that we do know about our system into machine learning. So I'm going to start by introducing the large ensemble testbed, which is just an idea that was developed by our group to test the data-based approaches within the model world. We use it to examine the strengths and weaknesses of both previous database estimates and new techniques that we're developing. So what is the large ensemble testbed? The idea is that in the real world, we're limited by the very sparse observations. But in the model world, we know the real PCO2 everywhere at all times. So the idea is that within an individual model world, if we sample the model at the same time in the same locations that we have real world samples, and we train and build a machine learning based function or model based on those samples, and then reconstruct PCO2 everywhere using our machine learning approach, we can actually compare the machine learning results to the modeled PCO2, the true model PCO2 and the true model CO2 flux at all times and all locations. So what we're using is actually 4 climate models. We're using large ensembles from CESM, the Canadian model, GFDL, and MPI. Each ensemble has 25 members, so there's a total of basically 100 models, 100 modeled versions of the real world. And it's simulating between 1985 and 2016 in these ensembles, but that doesn't actually correspond to real world 1985 to 2016, as these are Earth system models and are freely varying. So like 1997 does not correspond to 1997 in reality. So to look at this a little bit more closely, we have 100 different realizations of the world here on the left, where we have simulated PCO2 and simulated CO2 fluxes. Now we'll sample the model at the same time and the same locations that we do have these SOCAT observations. And again, we use approximately 80% of the data here to train and build our machine learning algorithm. In this case, a colleague of mine, Luke Gluggy, actually used the neural network that is in use by another data product to build the relationship between observations, which in this case come from the model, sea surface temperature, salinity, mixed layer depth, chlorophyll, and atmospheric carbon, to build that relationship between those model features and modeled PCO2. And then you can estimate PCO2 in all times and locations using the machine learning algorithm. But now you can compare it to the actual modeled world at all times and all locations and see how well we're doing. How well does this approach do? But it not only evaluates the approach that's taken, but like the limitations of the observations, right? Maybe the approach is really great, but there's not enough samples to yet constrain a certain location or time. So within this model world, we can also look at how well the PCO2 and the CO2 flux are captured as a time series at every point in space. So in the models, we have, of course, time series of PCO2 and CO2 fluxes for every grid cell. And we can deconstruct those time series into a detrended cycle, a seasonal cycle, decadal variability, and subdecadal variability time series, and see how well our techniques are capturing those different time scales. So Luke Gluggy actually did use this large ensemble testbed to evaluate a neural network database approach by Landschutzer. And what he found, or what they found, is that there was a very low mean bias in the CO2 fluxes when you compared the reconstructed CO2 flux to the actual modeled CO2 flux across the 100 members. However, there was really like large local biases, particularly in the Southern Hemisphere where there are not observations. Additionally, he found that the seasonal cycle, here we're showing correlations between the modeled seasonal cycle within the Earth system model, and then the reconstructed seasonal cycle from the machine learning approach. And you see that the machine learning approach does really well at capturing the seasonal cycle with high correlations. But as you go down in time, as you go to longer timescales, these correlations go down, and it's harder to capture that interannual to decadal variability using this data approach. So just as a summary, and then I'll pause for a few questions about the test bed. The database products are extrapolating very sparse measurements to reconstruct the air-sea CO2 fluxes. And from what we can test in the large ensemble test bed, they're likely doing very well at capturing seasonal cycles, but may have significant local biases, reconstructing fluxes and longer term variability. So how can we improve upon the previous techniques with what we do have? And how can we incorporate physical knowledge to improve our confidence in reconstructions? So here I'll pause for questions about the idea of the large ensemble testbed, just because it's used a lot. I want to make sure people understand what that is, or basics of machine learning is fine too.
It looks like Dan has a question.
Dan.
Yeah, quick question. You said 97 doesn't correspond to actually 97, and I understand that, but are these being forced with realistic CO2?
Yes.
So how do you deal with and so I guess there then out of sample predictions are not an issue because you have presumably the increase in CO2.
Right, but yeah, I mean, but you have fewer observations, like say in the early period when there's lower CO2. So it's something that's looked at more commonly now is like, how does this uncertainty, how does the error, the bias change over time based on what samples we do have?
Okay.
So I looked a little bit about that, and there was a greater bias earlier on in the period when there are fewer samples, because the machine learning techniques, don't have enough samples to say like when atmospheric CO2 was this low, how did the ocean respond? So it's less constrained, I guess I would say at that time.
Is that also a function of the number of predictors that you're using, where the more you kind of fine tune that, the more out of sample likelihood you have? That's possible. There are penalties in your machine learning for complexity. So you're penalizing more complex models and then testing how well they generalize. That's why you're keeping that subset of data out. So if it's not generalizing well, you want to go back and reevaluate how you're building your model. But there's some of that, yeah. Thanks.
Yep.
Any other questions while we're paused? No, you have a question.
Yeah, could you go back to the last slide, the ones that shows variability? Yes. So in terms of decadal variability, why is it over the tropic Pacific, it's still holding pretty well for the decadal ones compared to the others? Is it because it has more observation and you have more training data in that region?
I don't think it's actually, I don't like this color bar too much, but because I think it's a little deceiving, but I don't think it's actually sampling. I think it's about the processes in the model that are able to be captured with the sampling we do have, because there's more sampling, say in the subtropical North Atlantic and Pacific, and we're doing slightly worse there on decadal timescales. I think it's something I'm interested in. It is why we do well in certain locations and why we do more poorly in others. But I think it's more than just sampling that's going on there. I think it's actually processes that are being captured.
Okay, thank you so much.
Any other questions, or shall we keep going? Guess we should keep going.
Okay. So incorporating physical knowledge within machine learning is new in the geosciences. And so I'm just going to go into one example of how you can incorporate physical knowledge into machine learning. And so actually, this is a great example since you guys live right by Lake Mendota. So Kumar et al. In 2019 tried to reconstruct Lake Mendota temperature profiles. And they did this using a 1D lake hydrodynamic model and evaluated their process-based model. So in this case, having all the heat fluxes that we would expect, a more physical-based model, process-based model, I should say, and looked at how well the
the test data set did. So RMSE, root mean square error of the test data, and M stands for Lake Mendota, and S, they did the same thing for Sparkling Lake. And one thing I want to point out is that as you go up, the root mean square error actually goes down. So higher up on the spot is better. So they wanted to compare this to two different machine learning based approaches. So this is a typical process-based approach, but then they went and incorporated machine learning to see how well could we do. So there's 3 experiments here. One is the process-based model. The second experiment is using a neural network alone. And the third is adding a stability constraint to that neural network. So the machine learning algorithms are basically minimizing a cost function. What Kumar et al. Did is say the cost function also depends on whether or not you have heavy water on top of lighter water. So added a penalty to the cost function every time there was heavier water on top of lighter water. And what we find with the machine learning based approach, so the neural network or the deep learning without any physical based constraints performed better than the process based model. However, you could have unphysical results. And then the process guided deep learning model, what you'll see here in this case, is it performed even better than the neural network, but now had more physical results. So it not only performed better by having a smaller root mean square error, but it also builds confidence in the model. And I don't want to get too caught up in the different testing or training breakdowns, but the basic idea is not only did it build confidence in us believing the model, because now we know there's not heavier water on top of lighter water, it actually had a smaller root mean square error. So how can we incorporate some physical knowledge we have about the ocean carbonate system into our system, into our machine learning approach? And so in order to understand our approach, you need to understand the effects of temperature on ocean PCO2. I went over this a little bit, the solubility concept, but I want to go over it again just so we remember. If all else stays the same, if you increase temperature, your PCO2 is going to go up. And there's actually a quantified relationship between temperature and PCO2. So if you know a location's mean annual PCO2 or mean long-term PCO2, and you know its temperature, you can actually predict what PCO2 would be at a given temperature just using the 2. And that's if all else were to stay the same. But temperature also has indirect effects on the carbon cycle, right? So it sets up mixing and stratification, and those 2 processes may impact our surface ocean PCO2 greatly. So mixing can bring up nutrients and carbon from deeper waters and increase ocean PCO2 and reduce the amount of carbon that can be removed from the atmosphere. Or it can stratify and lead to biological productivity and drawdown of CO2. And these processes dominate in different regions. So in the subtropical regions, we have locations that are dominated by temperature. We have regions where the nutrients are low. And so even though there may be biological productivity set up by stratification, it's small. And so temperature is dominating in summer. And mixing is not bringing up that much carbon. So again, temperature is dominating in winter. But in the subpolar regions, we have these mixing processes and stratification and biology processes that are dominating. So what we thought we could do is try to make it so our machine learning algorithm doesn't have to learn both of these effects. So right now, if you reconstruct PCO2, say in that neural network-based approach, your neural network has to understand that temperature has both of these effects. Somehow that's got to be in the function, right? So in the PCO2 residual technique we developed, we thought, what if the algorithm only needs to learn the indirect effects of temperature on surface ocean PCO2? Because we know what the temperature effect is. That's well quantified. We can quantify it everywhere. We have a good understanding of the mean long-term mean of PCO2 at all locations from a lot of different data products. But that how it varies in time is the big question. So what we do in this technique is, instead of reconstructing the PCO2, we reconstruct the difference between the temperature-driven PCO2 and the observed PCO2. So I'm gonna walk through this a little bit. So we start with this map of the long-term mean of surface ocean PCO2 that's pretty well constrained. And here I'm just picking out a location in the North Pacific with this green star here. And now at that location, we have sea surface temperature from satellites. And we use the mean PCO2 and this sea surface temperature with the equation to calculate PCO2T, or the temperature-driven portion of PCO2, and that's in blue here. And then we have the observations of PCO2 at the same location. So they're in red dots throughout time at this given location. And so we want to know the difference between the observed PCO2 and this PCO2T, just the PCO2 that would be predicted if only temperature had changed. And so we have this residual here at the bottom. And it's just the difference between the two. So what does this residual look like? I showed you what the PCO2 observations look like. I want to show you what the calculated residual looks like. And so here on the left is the mean absolute value of this residual. And what I want you to take away from this plot is that it's very small values in the subtropical regions where it's dark blue. That's because these are temperature dominated regions, as we said. And so this residual is small. And in the subpolar regions, this residual is large and has a seasonal cycle. And on the right, you see the histogram of all the calculated PCO2 residuals from observations. You see it's nicely normally distributed, which is good for machine learning. So by season, on the left, show the Northern Hemisphere winter, and on the right, the Northern Hemisphere summer in the observations. Again, you see the same thing where you see small values in these subtropical regions, and they don't vary much in time here, similar colors in both seasons. And then you see very opposing colors in the subpolar regions. So how are we going to reconstruct this residual? We're using a technique called XGBoost to learn the PCO2 residual and build a function between sea surface temperature, salinity, observed chlorophyll, mixed layer depth, day of year is just DOI. N vector is just where you are on the globe, geographic location, and then atmospheric CO2, or the mixing ratio in the atmosphere. So we use the XGBoost algorithm to find the function between the nonlinear function between these observations and the residual. To get the reconstructed PCO2 that we need to calculate air sea fluxes, we add back the temperature-driven portion. And so what's XGBoost? Start with a simple decision tree. So XGBoost utilizes decision trees like a random forest machine learning approach. Just to understand what a decision tree is, I'm sure you've seen them all before, or maybe you didn't know the term for it, but it's basic if-then statements. If true, then this. If false, then this. A simple dimension tree, decision tree of one depth are shown here that make sense of the ocean data that we do have. So one example would be that if SST is less than 10, then I would add 5 microatmospheres to my estimate of the PCO2 residual. It's just a simple way. But decision trees are generally taller or more vertical than this and have a lot of if-then statements within them, so multiple layers. So you can imagine these one on top of each other and so on and so forth. So reconstructing this, we start with a single a single initial guess for PCO2 at all times and all locations shown here, right? So using XGBoost, we start with a single guess of that residual for all times and locations. And then we add decision trees one by one to reduce the difference between the actual observed PCO2 and our guess using the training data to build our model. And decision trees are added one by one until your training data is no more closer, but also there's a penalty for complexity. So you don't want to indefinitely keep adding decision trees. So there is a penalty for adding more and more decision trees. So that's called the regularization term. And XGBoost is just a long ensemble of these decision trees where your actual final guess is the sum of your initial guess plus the sum of all your adjustments, right? So these are very simply a sum of all these adjustments and your initial guess. So we're doing this with the residual. How do we know if it's an improvement, if our technique is any better than previous techniques? And so we are initially, as I said kind of before, using that large ensemble testbed to build our techniques. So we are evaluating our techniques within it. And in that, we build XGBoost to reconstruct PCO2 in one scenario. And then we also use XGBoost to reconstruct this residual instead. So two separate experiments here. And we'll evaluate the root mean square error for these two techniques. And all I want you to take from this plot is that in blue, if we reconstruct PCO2, our test data set and our error at places never sampled here in the lighter blue are higher than if we reconstruct the PCO2 residual. So here within our test data set, the error is lower, but almost more importantly, in locations that have never been sampled within the model world, our error is lower, reconstructing the residual. So what does this look like? So if on the left, if we reconstruct PCO2 and we look at our error compared to the model with those within those 100 models, right? The mean value of our absolute error is about 3 microatmospheres as a global average. Within the residual technique, this goes down to less than 2.5 microatmospheres. But really what you want to notice is that these regions in the Southern Hemisphere off of South America here are really reduced in this subtropical Southern Hemisphere here. And how about in longer term correlations? We looked at previous techniques and we weren't doing that well, capturing longer term variability. So if we look at the correlation, the decadal correlation in the PCO2 technique, as well as the decadal correlation in the PCO2 residual technique, you'll notice it's deeper red, which is better values, higher values in the residual technique. And here's the percent change between the two techniques. And you again see in these poorly sampled regions of the Southern Hemisphere subtropics, you see significant improvements in the decadal correlation. So we're doing better at capturing that longer term variability in this technique. So this is in the large ensemble testbed. What about when we apply this technique to the real world observations? So again, we've reconstructed PCO2 in the past. We've been working on that for a long time. And then we're also going to look at the error in PCO2 when we reconstruct that residual. And we see that within our test data sets, we do see improved statistical metrics here with a smaller root mean square error, a smaller bias, a smaller mean absolute error, and a higher correlation with observations. So we're happy with our technique, and we've actually used it to reconstruct historical CO2 fluxes. Here on the left is showing the mean air sea CO2 flux estimated by the technique. And on the right in magenta is the estimated CO2 fluxes for the recent past. What we'll notice is that these are other data products here in the other colors, and that they're similarly in magnitude. One thing, I didn't plot in here the biogeochemical models as well, but one thing you'll notice is this, as this is in the opposite direction, more negative is a bigger CO2 sink into the ocean. You'll notice that this magenta color is on the lower end of the sink in the last decade, in closer agreement with biogeochemical models than some of the other data products, and some are not shown here because they're much larger sink. And we have confidence in our approach. It's more physically based, and it's shown to perform well in the large Ensemble test bed. So now we're trying to utilize this approach to look at some sampling and uncertainty studies that I want to touch upon here. In our first, just to make note of the SOCAT sampling by year, I kind of mentioned this briefly with Dan's question, is that we have a lot more observations in the more recent decades. So you'll notice after the 1990s, the number of samples really doubled per year by 2006. So the question, we work with NOAA scientists and they want to know the value of the observations. It's very costly to observe. So what is the value of all these observations? So the initial question we asked is, what if the 90s never left us? So in other words, what if we continued sampling like the 1990s? So in red here, I'm showing what sampling would have looked like if we never ramped up sampling. Instead, we sampled like 1995 to 1999 over and over and over again. So essentially cutting the number of observations in those years by half. So how would this change our sampling? So I'm just simply applying the same time and location that we observed in 1995 to 1999. And then in 2000, we're observing just like we did in 1995. In 2001, we observed like 1996. So in most locations, it reduces the number of samples, but there are some locations where we sampled in the 1990s and we haven't gone back. So there are places where, like the Indian Ocean, where we have some red, where we have more samples. Excuse me. But the biggest takeaway is that the Southern Hemisphere, these are lightly colored, hard to tell, but these are all fewer samples. And that the subtropical regions are much less sampled after the 1990s in this technique. So how do we do if we test this in the large Ensemble test bed? So in this case, we build our algorithm based on this reduced sampling, and we test it against the real modeled world. So we're not doing this with the observations quite yet. We're doing this in the model world. So can we still capture the CO2, the PCO2 cycles of the ocean? And so in this case, we're looking at how well we can capture the seasonal cycle if we're only sampling like the 1990s throughout the 2000s. So on the right-hand side, we're looking at the correlation difference. So the difference between if you had sampled basically half as many times versus the real world sampling. And what you'll notice is that there's really no difference in our ability to capture the seasonal cycle of PCO2 in the subtropical regions, even in the poorly sampled southern subtropical locations. And that's because the algorithm is learning those relationships. It's a small residual that needs to be reconstructed, and PCO2 is constraining most of that. And then you also notice you see this red in the Indian Ocean. So it's a very poorly sampled region, but sampling like the 1990s actually increased our sampling there. So we did see an increase in our ability to reconstruct the seasonal cycle there, which is interesting. But you'll also notice that outside of the subtropics, we see a great loss in capturing even the seasonal cycle of PCO2 because we have reduced our samples. So this is a good thing for motivating sampling, but also where should we motivate? Where should the sampling go based on the techniques we're using? So if we look further at variability from year to year, now how well are we doing at capturing interannual variability? And here we're looking at the percent difference in the correlation between the two techniques. So here blue means that sampling like the 1990s gave you a reduced ability to capture interannual variability of the ocean PCO2 cycle. And again, what you notice is that increased sampling really helps everywhere capture the interannual variability, particularly though out of the subtropics in the Southern Ocean, where we see really dark blues almost in a line across here. And then in the subpolar North Atlantic, we see deeper blues as well as we're out of this temperature-driven region. And so some of the key takeaways I want you to have from this is that we are able to incorporate some physical knowledge into a machine learning based approach. So an approach typically thought of as a black box. In this case, we are looking at giving it some of our knowledge, but then also some things I haven't focused on in this talk is looking at the interpretability of that model that is built. Using our new PCO2 residual technique, we reconstructed the air-sea carbon dioxide fluxes, and estimates are within reason, within agreement with the Global Ocean Carbon Budget 2020, which is good news in that we're not that far off from the models, and we're very close to some of the data products, the ones I showed there. So we're narrowing that gap in time. And now we're just beginning to utilize this approach to look at the importance of sampling and sampling locations, but also working with some NOAA scientists to look at like the values of individual cruise tracks on the reconstructions. And with that, I will take questions. Thank you very much for your time. And I have some extra slides for certain questions that might come up, so feel free to ask away.
Thanks so much for the talk. And I'm seeing lots of little virtual applause hands. I'll actually applaud. Yay. Questions? Oh, there's lots of little hands now. Grant's raised his hand.
Hi, Grant.
Hi, Val. So I'd like to go back briefly to the model that you are training to estimate PCO2 from atmospheric variables, and there was a number mentioned that were obvious, like the atmospheric CO2 and the mixed layer depth and temperature and a few things like that. And there's one that I didn't see that I was kind of curious to hear your explanation of why it's not really important, and that is the mean wind speed, which I would think would affect the turbulent transfer and would affect the rate at which the PCO2 can move toward equilibrium with the atmospheric CO2. So
yeah, no, I think that's a great question. Yeah, no, and that's one I'm actually thinking about adding. So historically, just other scientists haven't used that one, but there's very good reason to include it, and for the exact reasons you're saying, particularly since the mixed layer depth is only a climatology that we have. So we don't have year-to-year variations in that, whereas wind could be a proxy to some of that. And I'd love to get into adding it and seeing where that, what changes we see with having that. One other scientist recently did test adding that and found some improvements in his reconstruction. So I'm hopeful that we would see the same as well. So no, that's a great question. It's evolution in time, really, of these techniques and thinking about what we have. I don't have a great reason for why it wasn't in our technique to start. I think it should be added. Does that answer your question?
Yeah, thank you very much.
Okay.
Next question. Chen Nuo again.
Yeah, so by you introduce one physical knowledge into your machine learning algorithm, does that bring up another or more physical understanding of your model? So does the model provide more physical knowledge, or it is constrained by other physical knowledge at the same time? Just by
Sure. So yeah, let's see here if I can go. So one thing I did do is, can you see my screen still when I went out of this presenter mode?
Yes.
Okay. So I didn't think I would have time for it, but one thing I have been doing is looking at the interpretability of the model. So the model that is built by the algorithm, like how much would we believe it or not believe it? What physical properties is it capturing? Previously I attempted to, instead of reconstructing this residual, instead was reconstructing like delta PCO2, which is the air sea difference in that partial pressure. So when I reconstructed delta PCO2 and then tried to look at my model, I found that there were certain features that didn't look like they were physically, like that the response the model had to those features was physically unrealistic, I should say. So I've been looking at the impact of the different features on the reconstructed, in this case, residual. So it doesn't directly translate to PCO2, right? It's the residual. We have to keep that in mind. And I have been seeing good patterns of how the, in this case, is this the impact of sea surface temperature within one model realization on the reconstructed residual. And so we do see much larger residuals in the subpolar regions and higher values, meaning the residual needs to be higher in the subpolar regions, which is what we would expect. So I'm getting into deconstructing that, but also looking at the impact of atmospheric carbon dioxide on the reconstructed values and seeing what we'd expect here too, that it's a homogeneous in contrast to the SST, where we see large variations in space of the impact. We see a more homogeneous impact of the atmosphere onto the ocean. And the impact is saying when atmospheric CO2 is higher, our residual is higher, which is also what we would expect. So it's increasing over time. So I am looking at the interpretability of the created models and finding that it is more physically what we would expect than in previous techniques I've used, if that makes sense.
Yeah, it makes sense.
Okay.
So I have another question about, because the subtropical and kind of subpolar region have two different physical schemes. Is it possible to model them nonlinearly in machine learning algorithm?
You could do them separately. Is that what you mean?
Could you do that in the same model instead of separately?
So they're using the same model right now. It's just that they have very different kind of targets because the residual is so small in the subtropical regions and the residual is larger in the subpolar regions. So right now I am using one model for all of the regions. You could also, some scientists might opt to create a completely different model based on region. Then you just have the task of merging them. How do you smooth where they meet and things like that.
Okay.
But in this case, I'm using one model for both regions. It's just that the model itself knows where it is in space and time and adjusts accordingly.
Right. Thank you.
Okay. Mm-hmm.
Do we have another question?
Sure.
Or am I going to ask a question?
Sure.
Oh, Evan's got a question. Evan takes precedence. Evan, we can't hear you. I can hear you next door, though. Evan, can you hear us? If you want to come next door, I'll open my door and put a mask on.
While Evan's coming next door, oh, you got it, Evan? All right, while he's coming next door, I'll ask a question.
Sure.
Yeah, the last question that Noah Chen was asking, I guess, is kind of what I was thinking as well, that, you in a sense, it'd be nice to be able to break this down by, say, biome or type of,
Yes.
situation, which you kind of do by having chlorophyll as a predictor and SST.
Sure. I actually, I actually did do this with another variable as the biome.
Yeah.
And we had a data science institute scholar do it a separate model per biome as well. So we tried both adding biomes as a feature and modeling separately by biome. And we did see minimal improvement, and that could be because we still we're observation limited, of course. So it could be maybe there is a bigger gain that we just can't see yet based on the observations. But because it was such a minimal addition, we decided to not add to the complexity of the model. But that's one thing that I do wonder, as we get more samples in some of these really poorly sampled regions, will that be more justified?
I guess I kind of wonder if you're using SST everywhere, how much of that is just,
that captures some of it,
or is that just capturing, almost latitude as a,
we do have latitude as a feature. Those geographic variables have basically the sign of the latitude, the sinusoidal curve.
Thanks.
Okay, Evan's question.
Hi Val, great talk.
Thank you.
I had a quick question about you mentioned the regularization factor that you were using.
Sure.
For the neural network. I was wondering what the shape of the penalty is, because you mentioned that it's a more complex outcome would be penalized, but I imagine that there's some sweet spot, and I was wondering if you've done any testing with different types of penalties, like a 1/x or something.
Yeah, no, I haven't done specific testing with the different regularization terms. I think that would be really nice to spend the time doing that. I haven't yet done that, but there are a lot of approaches to that, and I'm just using a basic regularization term right now. That'd be something, if something a lot about too, is something we could talk about offline as well, but I don't have a ton of knowledge on all the different variations of the regularization term.
Gotcha. Yeah, I guess that kind of answers the second part of my question, which is are there standards that are used in the field? Yeah,
I'm just using a standard, and so I can get you all the details about that offline if you'd like. But there's just a standard term that I'm currently using.
Okay, cool.
I think I saw Ian had his hand up briefly. Do you still have a question? I think we'll make that the last one. Go for it, Ian.
Thanks, Liz. Maybe this is a domain uninformed question, but since you're observation limited, is there a way to use some data augmentation technique that might enhance your generalization and approach some of those differences in residuals that you were seeing?
I think, do you mean sort of
looking at the data nearby that you do have and modeling and sort of getting.
I guess
What
to
exactly?
clarify a little bit, like the idea of creating some synthetic data points so something that the model, basically generate new data and see if that would actually help I guess you would have to have some kind of reasonable, within the realms of possibility, fake data, and then see.
Yes.
The goal would be to see if that generalizes more.
Yes, I see what you're saying. Or you could withhold more or something. I'm trying to get at some of that within the test bed, and we've done a little bit of that where we pretended to have more data. So in the test bed, you can do that with the model data and say, well, what if we had sampled the Southern Ocean for 10 years instead of for 1 year? And we do see in those cases, don't think I have that. Don't think I have that slide. That's what I was looking for. But we do see an increase in the skill, not only right there in the Southern Ocean, but also throughout the globe, as you see primarily in the high latitudes where you see just a better model being produced. So I have thought about that, like, with the real world, going into that 90s experiment again and being careful about not making certain locations have more samples like I currently have my current experiment and things like that. Like, how would I quantify the importance of sampling? But what you're getting at is more, I haven't done exactly that, creating synthetic data. Instead, we've kind of, any additional data we have, that's outside this database, we use it to say, how well did the model do? And there's not that much of it. There's some at Bermuda, at Bats, at Hawaii, and a few more ocean coverage stuff with GLODAP, which has higher uncertainty. But anyways, I think that would be an interesting approach that I haven't tried yet.
Cool, thank you.
Mm-hmm.
Let's give one more round of applause for Val.
Thanks, guys.
And I'm seeing something in the chat here.
I think it's mostly just accolades.
Yeah.
Okay. And feel free, anyone's welcome to email me or reach out with any other questions that come up or interest in the technique or what I'm doing or ideas, anything. So feel free to reach out.
Awesome. Thanks, Val.
Thank you.